So one of the most important aspects to know about a compound is its molecular shape. And it's important to know that even though we draw molecules in two dimensions, because that's what we're limited to on a piece of paper or on a screen, um, these molecules, though, are three-dimensional objects. And how they occupy three-dimensional space is very important to its properties, chemical and physical properties, as well as how it reacts. And these molecules don't just take any sort of random shape or, whatever our imagination can conjure. We use a model called VESPER to predict the shape of central atoms. And I want to highlight here that it is possible and very, very common, actually. Molecules can have a variety of different shapes because the atoms are different throughout a molecule. So the bigger the molecule is, the chances are much, much higher that one side of the molecule will have one shape, another portion of the molecule will have a different one, and yet a third portion will have something completely different. So being able to recognize what the requirements are for a particular shape is going to be what we're going to focus on for a little bit. Now, what is this VESPER theory? VESPER stands for valence shell electron pair repulsion theory. And that's a big fancy way of saying electrons in lone pairs or bonds repel each other. All right, so for example, on paper, I can draw carbon dioxide like this. Maybe I should kind of show a little bit of an angle there between the oxygens. But we're dealing with electrons. There's electrons in the bonds, there's electrons in the lone pairs, and electrons, they all have the same charge. They're all negatively charged. And they do not like to be close to each other. So what VESPER theory does is it says it's going to spread out, the electrons will spread out, and the molecule will adopt a shape so that it maximizes the distance between electrons to minimize the repulsion between them. So the way carbon dioxide will spread everything out as far as possible is to put an oxygen on one side and an oxygen completely 100 degrees, 180 degrees away from it. This is as far as possible. And in fact, we give that shape a name. We call it the linear shape. I'll go a little bit more deeper into this in a little bit. Now, lone pairs will do this as well. So let's take sulfur dioxide as an example. Okay, so now I have a lone pair here. It does not like to be close to those bonds. And so the best way for sulfur dioxide to spread out to maximize the distance between the lone pair and the bonds is to adopt this sort of shape. It's not linear, it's not like carbon dioxide. But we'll get to what kind of shape we would call this. So to determine the shape of a molecule, number one, you have to know the number of electron dense areas. I refer to these as like regions of electron density. And they're simple to identify. Those are lone pairs and bonds. Now, one thing I want to highlight, a common mistake students make when kind of counting these regions up, is that a single bond is one region of density. A double bond is one region of density. A triple bond is one region of density. Even though there are more and more electrons there in a triple bond or a double bond, we always count them as just one region of density. Now, the second important thing to know is how many of these regions are lone pairs and how many are bonds. Knowing that number will guide us to the proper molecular shape. Let me kind of show you a very important table to know. And I would start committing something like this to memory. But you can kind of see here that based on the number of regions of electron density, the shape of the molecule can change. And also depending on how many lone pairs there are, the shape can be slightly different. So let's go into our first shape here. We'll start from easiest and kind of go to more complex. So the first one we're going to look at is linear. This is characterized by two regions of electron density. Now, to preface all of this, and this is the foundational thing for all of the shapes, so I'll put it up here at the top. You only consider the shapes of central atoms attached to at least, circle, highlight, star, that, at least two other atoms. Now, in a linear shape, we have some central atom and it's bonded to two other things. No lone pairs. And you notice there's two regions of electron density here. One, two. And the bond angle around this atom A is 180 degrees. You need to know that. You need to know that bond angle there. So an example of this I've kind of highlighted earlier is carbon dioxide. If you look at carbon dioxide, around the carbon, there are two regions of electron density. I know they're both double bonds, but this is one region, that's a second region. So I go over to my table, I see that two regions of density, the only thing it could be is linear. Another example of this is BeH2. No lone pairs around beryllium. There's two regions of density, a single bond and a single bond. And so we would consider this to be linear. One more example. This is the compound acetylene. If we just look at this carbon first, you can see around that carbon, there's a single bond and a triple bond, two regions of density. So this carbon right here, we would say has a linear shape around it. We would say the same thing for the second carbon. That carbon has two regions of density around it. So we would say that it has a linear shape. Now the next in our series is trigonal planar. Now, at this point, you'll notice that in the table, there are two possibilities for this. And the reason for that is I have to distinguish between two categories of shapes called electron geometry and molecular geometry. Electron geometry is the shape that also is concerned with lone pairs. It includes the lone pairs in the factor of determining the shape. Molecular geometry is more concerned with just the position of the atoms. And it doesn't really take the lone pairs into account. It ignores them. And molecular geometry is much more commonly used. And in fact, like if I put this on an assessment or a homework or anything like that, if I just say, what is the geometry around this atom? I'm asking you for the molecular geometry. If I want the electron geometry, I will let you know. So the first one in this category is we have three regions of density with no lone pairs. So here's a nice generic example. Some atom surrounded by three regions of density. Now the bond angle for this is 120 degrees. Make sure you know this. Now a couple examples of this. This is the compound borane, or BH3. Borane's one of those weird ones that's okay with 6-valence electrons. I highlighted those exceptions earlier. But there's three single bonds around it, three regions of density, no lone pairs, so we label this as trigonal planar. Another example is the compound formaldehyde. Now, one thing I do want to point out, I mean, if you look up, Google the bond angle formaldehyde, this bond angle here is going to be a little more than 128 degrees, just slightly, maybe a couple degrees, if any. And the reason for that is double bonds, since there's more electrons, repel more than single bonds. Now, if there is a lone pair present, then the shape, or at least the name of the shape, changes. So we have two groups of atoms and a lone pair. Lone pairs repel more than bonds. And so what happens here is this bond angle here is greater than 120 degrees. And this one here is less than 120 degrees. Since lone pairs repel more than bonds. Now, the molecular geometry, we would say, is bent. The electron geometry still falls under trigonal planar. Now, I showed an example of this earlier with sulfur dioxide. Here's the Lewis structure for sulfur dioxide. And hopefully you're kind of seeing why it's important to know how to draw these correctly. Because if you don't draw them correctly, then you won't have the right number of electron regions. And if you don't have the right number of electron regions, then you will be predicting the incorrect shape. If you predict the incorrect shape, then you are probably going to predict the wrong properties and reactivities. So notice here in sulfur dioxide, there are three regions of electron density. And since one of those regions is a lone pair, we would say the geometry for sulfur dioxide is bent.